In section 11.5, we discuss a system of parallel Gaussian channels. Consider a system consisting of k independent channels, where the ith noise variable, Zi, is a Gaussian random variable with mean 0 and variance Ni, and Z1 up to Zk are mutually independent. The total input power constraint is expectation of summation I equals 1 up to k xi square is less than or equal to p. The channel capacity with input power constraint p is equal to the supremum of the mutual information between the input vector x and the output vector y over all input distributions f of x such that the expectation of summation I xi square is less than or equal to p. Intuitively, C of p is equal to the maximum over all p1, p2 up to pk such that summation I pi is equal to p 1/2 times summation I equals 1 up to k log of 1 plus pi over ni, where the input random variable for the ith channel is the Gaussian random variable with mean 0 and variance pi, and the input variables x1, x2 up to xk are mutually independent. Note that in the above formula, 1/2 times log of 1 plus pi over ni is the capacity of the ith channel when the input power is pi. And summation I pi equals p means that the total input power is exactly equal to the total input power constraint p. A formal justification for the proposed formula for C of p is the following. Let pi equals the expectation of xi square be the input power of the ith channel. Consider the mutual information between the x vector and the y vector, which can be written as the differential entropy of the y vector minus the differential entropy of the noise vector. H of y is upper bounded by summation I equals 1 up to k, the differential entropy of yi by the independence bound, and h of z is equal to summation I equals 1 up to k, the differential entropy of zi, because all the noise variables are independent. Now, the differential entropy of yi is less than or equal to 1/2 times log of 2 pi e times the expectation of yi square, and the differential entropy of zi is equal to 1/2 times log of 2 pi e times ni. Upon cancelling the 2 pi e's, we obtain 1/2 times summation I equals 1 up to k log of expectation of yi square minus 1/2 summation I equals 1 up to k log of ni. Now, expectation of yi square is equal to expectation of xi square plus expectation of zi square, because zi is zero mean. And the expectation of xi square is equal to pi, while the expectation of zi square is equal to ni. Upon combining this logarithm and this logarithm, we obtain 1/2 times summation I equals 1 up to k log of 1 plus pi over ni. Note that the inequality 1 is tight when the input random variables xi are independent, and the inequality 2 is tight when xi is equal to the Gaussian random variable with mean 0 and variance pi. Therefore, the maximization of ixy becomes the maximization of summation I log of pi plus ni in equation 3. In summary, the capacity of the system of parallel Gaussian channels is equal to the sum of the capacities of the individual Gaussian channels with the input power optimally allocated. Consider maximizing the objective function summation I log pi plus ni subject to the constraints summation I pi is less than or equal to p and pi is greater than or equal to 0. We first attempt to solve this maximization problem using the Lagrange multipliers. We apply the method of Lagrange multipliers by temporarily ignoring the requirements that pi must be greater than or equal to 0. Observe that in order for summation I log pi plus ni to be maximized, summation I pi must be equal to p because log pi plus ni is increasing in pi. In other words, if summation I pi is strictly less than p, it is possible to increase some of the pi's to increase the objective function. Therefore, we set summation I pi equals p. Let j equals summation I equals 1 up to k log of pi plus ni minus mu times summation I equals 1 up to k pi, where mu is a Lagrange multiplier. Differentiating j with respect to pi, we obtain partial j by partial I equals log e divided by pi plus ni minus mu. Setting partial j by partial I to be 0 and solving for pi, we obtain pi equals log e divided by mu minus ni. Now observe that log e divided by mu does not depend on I. Upon letting nu equals log e divided by mu, we have pi equals nu minus ni, where nu is chosen to satisfy the power constraint summation I pi is equal to p, that is, summation I equals 1 up to k, nu minus ni is equal to p. This solution has a water-filling interpretation, which is illustrated in the figure. In this example, we have 3 channels with noise powers N1, N2, and N3. Imagine that we have a reservoir with an uneven base whose height is specified by the values of N1, N2, and N3, and we are to pour water into the reservoir with a volume equal to P. The water level is denoted by nu. We note from equation 1, that is Pi is equal to nu minus Ni, that Pi is greater than or equal to 0 if and only if nu is greater than Ni. That is, the water level is higher than Ni. Thus, Pi is greater than or equal to 0 for all I if and only if nu is greater than or equal to Ni for all I. Under such a situation, although in setting up the Lagrange multipliers, we have ignored the requirements that Pi must be greater than or equal to 0, it happens that this constraint is satisfied, and so the Pi's as given in equation 1 is the solution to the maximization problem. On the other hand, if for some I, nu is less than Ni, then Pi equals nu minus Ni would be negative. Under such a situation, the Pi's as given in equation 1 cannot be the solution to the maximization problem. Nevertheless, the form of the Pi's given in equation 1 suggests the general solution to be proved in proposition 11.23. By means of proposition 11.23 to be proved, which is an application of the Karush-Kuhn-Tucker condition, or the KKT condition, we obtain that in general, C of P is equal to 1/2 times summation I equals 1 up to k log of 1 plus Pi star divided by Ni, where P1 up to Pk is the optimal input power allocation among the channels given by Pi star equals nu minus Ni plus for all I, where x plus is equal to x if x is greater than or equal to 0, and is 0 if x is less than 0. With nu satisfying the constraint summation I equals 1 up to k, nu minus ni plus is equal to p. Note that for each I, if nu is greater than ni, then pi star is equal to nu minus ni. If nu is less than ni, then pi star is equal to 0. The set of optimal input power allocation continues to have a water-filling interpretation. In this example, we have 4 channels, 1, 2, 3, and 4, with noise powers N1, N2, N3, and N4. Here, the water level nu is lower than N4, and so P4 star is equal to 0. In other words, when the noise level of a channel is too high, we do not allocate any power to that channel. We now discuss proposition 11.23, which says that the problem, for given lambda I greater than or equal to 0, maximize summation I equals 1 up to k log ai plus lambda I subject to summation ai less than or equal to p and minus ai less than or equal to 0, has the solution ai star equals nu minus lambda I plus for all I, where nu satisfies summation I equals 1 up to k, nu minus lambda I plus equals p. Here, ai plays the role of pi, and lambda I plays the role of ni in the context of the parallel Gaussian channels. Note that the inequality in equation 2 is written in this form in order to cast the maximization problem into the standard form. The proof of this proposition can be skipped at the first watching of this video. We will prove the proposition by verifying that the proposed solution satisfies the KKT condition. Here, we will not explain how to set up the KKT condition. If you are not familiar with the KKT condition, you can look it up in a book on optimization theory, or you can look it up on Wikipedia. Verification of the KKT condition is done by finding non-negative values, mu and mu I, satisfying the following equations. Where mu is the multiplier associated with the constraint in equation 1, and mu I are the multipliers associated with the constraints in equation 2. Consider the constraint summation I nu minus lambda I plus is equal to p. To avoid triviality, assume that p is strictly positive, and so nu, the water level, is also strictly positive. And observe that under such a situation, there exists at least one I such that ai star is greater than 0. This is because ai star is equal to nu minus lambda I plus. For those I such that ai star is greater than 0, as mentioned, there exists at least one such I. Equation 5, which says that mu I times ai star is equal to 0, implies that mu I is equal to 0 because ai star is not equal to 0. Since ai star is equal to nu minus lambda I plus, and ai star is greater than 0, nu minus lambda I plus is equal to nu minus lambda I. Or, ai star plus lambda I is equal to nu. Then in equation 3, we have mu I equals 0, and ai star plus lambda I equals nu, which implies mu is equal to log E over nu. And this is greater than 0 because nu is greater than 0. For those I such that ai star is equal to 0, we have nu less than or equal to lambda I, because ai star is equal to nu minus lambda I plus. In equation 3, which is reproduced below, we have ai star equals 0 and mu equals log e over nu. And from this equation, mu I equals log e times 1 over nu minus 1 over lambda I. And this is greater than or equal to 0 because nu is less than or equal to lambda I. In summary, from equations 3 to 5, we have obtained mu equals log e over nu, which is greater than 0. For those I such that ai star is greater than 0, mu I is equal to 0. And for those I such that ai star is equal to 0, mu I is equal to log e times 1 over nu minus 1 over lambda I, which is greater than or equal to 0. Thus, we have obtained non-negative mu and mu i's satisfying the KKT condition. This completes the proof of the proposition.